Okay, everyone. So we last left off with this kind of convoluted, very convoluted sentence that is going to let us calculate our standard deviation. So as I noted in the last video, the way that we're going to do this is by working backwards. So let's start with the last clause of the sentence, which is the deviation of the values from their average value. Okay, so let's start substituting actual terms, which is, what is the average value? Well, we know that the average value is otherwise known as the mean. Okay, we've already got the mean, so that's a good place for us to start. So now we're saying the deviation of the values, right? So that's the values in the data set, from their average value. So what is deviation? Deviation means difference. Okay, what is the difference of each value from the average value? Well, difference in arithmetic is just subtraction. So the way we're going to do this is we are simply going to say, I'm going to say diff from mean. Okay, I like labeling things very literally here. So the first thing that I'm going to do is I'm just going to calculate the difference between each value and the mean. So I can do that as we have been. I start with an equal sign. I'm going to point to a particular value. I'm going to hit the subtract sign, and I'm going to point to the mean. Okay, that's the difference between that value and the mean. Now, I want to do this for every single cell. Fortunately, if I copy and paste this formula down, Microsoft Excel is clever enough to actually move the references down. So in other words, because I was in cell B3 here and I put in this formula that pointed to B2, if I copy that formula to I was in C2, I pointed to B2. If I copy it to C3, it's going to then move that to shift to point to B3, right? So that's great. However, as some of you may know, as you may notice, right, this actually has a little bit of a problem. This one looks fine, but what about this one? It's actually the same value. Well, of course, that's because at the same time that I pointed to B2, I also pointed to K2, which has the mean, which is good. The problem is that I don't actually want that reference to K2 to move, right? I want it to always point to K2 because otherwise I'd have to copy my mean into lots of different cells in order to get this to work. So Excel, just as it's clever to move down that reference, also has a mechanism for locking a reference, right? So basically this gives us a way to say, listen, I know that I'm going to copy this formula, but this one cell reference, right, this column and row reference, I want you to keep the same. And we can actually lock these things independently, so we can lock the column or the row or the column and the row. And the way that we do that is with the dollar sign. So if I precede this K, I'm going to lock both of them, okay? So I'm locking column K, so $K means always reference K. $2 means always reference cell 2. So now, if I don't put the dollar sign on the first part, because that, of course, is my individual data value, I want that reference to move. But if I have that K2 now, with the dollar signs, now I can paste this and I get something much more sensible. And you notice, of course, that some of these values are negative because they are below the mean, right? Unsurprisingly. That's perfectly all right. It's one of the reasons why we have to take an extra step, which is to square them, right? Because a standard deviation is always going to be a positive value. The quickest way to handle the issue of negative values when you need a positive outcome is to first square a bunch of stuff and then take the square root later. So that is actually exactly what we're going to do. And you can see this when we look back here, we can see that it says, actually take the squared deviations, right? So no surprise there. I'm going to flip back to my worksheet here, and I'm going to call this squared diff, okay? And how do we get the square of something? Well, we simply multiply it by itself. Again, here I can just use the cell reference twice in the same formula, so I can say equals C2 star C2, right? And in this case, I can just copy it all the way down because I don't have to worry about locking any references, right? I'm only referring to sort of the cell next door when I do this. So I would say I have a set of very large numbers now. That's okay. I just squared a bunch of very large numbers. That's to be expected. So now it's asking me for the average of those squared deviations? Well, we certainly know how to calculate an average. So I'm just going to say over here, I'm going to put average, or I could say mean of squares. Whoops, squares. It's wrapping because I'm running off the page here. Okay, so how do I calculate the mean? We obviously know that answer. We simply add them all up and divide by the number of readings. So I can do this exactly the same way. I can say that I have been. I can say sum, right? I'm going to choose all of these and divide by 19. And now we have the average of the squares, right? Still a pretty big number. So back to my formula here, and then it just says taking the square root of the average of the squared deviation. So I've done everything except take the square root. So in this case, I can actually just label this, I'll label this SD for standard deviation, is just going to be the square root of this number. Okay, so that's my standard deviation. Now remember our discussion about precision. Really the value that I'm dealing with here is, at best, is going to be like 50,364, right? Because I have a decimal, I will round it up. So if I was asking, so when you report the standard deviation, you're obviously not going to report past the one column. You're going to round to the appropriate ones column, and that's going to be your standard deviation, because we can't say that, oh, now we know to a precision of 5 decimal places simply because we did some math. So that's great. That was one of our main tasks, was to determine the standard deviation. Now again, that standard deviation is interesting in part because it serves as a unit for talking about how much of a data set is going to be between two particular values, right? And so the last thing that I'm going to do is I'm going to calculate what's called the z-score or the normal score or the z-index, lots of different names for the same thing, which is just the number of standard deviations away from the mean a particular value is, okay? So all it is saying, where would it fall if I was using this as the x-axis, these standard deviations? Would it be 1.5? Would it be 2.5? Would it be -2? Whatever, right? Like, that's all I'm doing, is I'm kind of grading each data point based on where it would fall along this sort of -4 to 4 standard deviations path, okay? And so the way that I do that is quite simple, because again, we're using it as a unit, which means it's really just the denominator. All we need to do is divide. So I'm going to call this z-score, okay? And so in each case, now the thing that I'm calculating the z-score for is not either of these, right? These were both intermediary step calculations. It's the actual data point, right? So in each case here, what I'm going to do is I'm going to say, look, I want to know what that is divided by the standard deviation, okay? And I'm going to leave the standard deviation for the purposes of this calculation. I'm going to leave it untouched, right? I'm not going to round it because I'm still doing math. So I don't want to round and then use that rounded number to divide another number, right? I always want to do all my rounding at the end of a particular calculation. So I'm going to say it's K4. And again, in this case, because I want to reference this and keep the reference at K4, right? I want the B2 to become B3, B4, B5, etc. But I want to keep that K4 fixed. I'm going to add my $signs here. And now I can just copy and paste all the way down. Okay. So now what we see is that this is where actually the sort of bifurcation of our data set becomes really apparent, because what we should have, if it was a normally distributed data set, what we should have is 68% roughly of our data points, 68.25% of our data points should appear within one standard deviation of the mean. In this case, we have something very unusual, which is that we do have a bunch of them, right, that appear within one standard deviation, but they're barely, they're very, very close to the mean, right? They're like way less than a standard deviation. Then we have a lot of stuff that is wait a second, did I do this right? No, I did this wrong. Ha! Wrong one. I don't actually want to look at the number. I want to look at its difference from the mean. There you go, right? I actually want to, because I was like, why are none of them negative? Obviously, we should have some negative numbers because not every reading is larger than the mean. Let's try this again, okay? Okay, that looks a little bit better. Now, we still know that we have a pretty messed up data set, however, and that it's not normally distributed. However, that was a red flag, right? So that's the gut check moment. So let me just leave my error in place here, right? So started talking about why this was wrong, and what did I notice? Well, what I noticed was none of the values that I was getting were actually negative, right? And that's even worse, right? Than not getting that, or even more surprising. I guess it's not worse, it's not good or bad. It's even more surprising than not having than not having them be normally distributed, which frankly we really don't expect most things to be normally distributed. We kind of expect the opposite, that it's going to be skewed in some way. But what I noticed was that every value, they were only positive, right? So that was the red flag to me that something was wrong. And in this case, the thing that was wrong was that what I need to be measuring is not the value itself in terms of the standard deviation. I need to be measuring its distance from the mean in terms of the standard deviation, right? Because that's what I'm looking at. I'm looking at how far is it from this mean, not if I had that number and I happen to divide it by the standard deviation, what would that give me, right? So that was the error of my ways. And so what I really should be looking at is, let's go to a top value so it's a little bit more intuitive, right? What I really should be looking at is not the value itself, but its difference from the mean, okay? And so now if I do this, I get something that is still not standard, which is fine. Again, most things aren't. But I get something that's more sensible because at least I have some negative values, right? At least I'm starting to see a pattern that makes a little bit of sense. Now, again, what I'm noticing here is that almost all of the data, right, is within one standard deviation of the mean. And that also is pretty unusual, right? If we actually had a standard distribution, we would see something much closer to the spread that we expect, which means that about 30% of our data should be between 2 and 3 standard deviations from the mean between 1 and 3 standard deviations away from mean per this graphic, right? So we know that there's something wonky going on. Then again, we knew that anyway because we're humans and we have thinking brains, unlike computers. And so we can do things like notice that something appears to be wrong with the data set. So again, we'll go over in class some examples. I'm going to try and post some examples of when you would use this. I think the thing that the thing that comes to mind for me is the fact that, and this is actually one of the reasons why sometimes professors grade tests on a curve, right? Or teachers grade tests on a curve, is because the idea is that you're trying to, one, insist that your test is written correctly and therefore you should see this perfect Bell distribution, but it also lets you compare performance across sets of students, as an example, right? Or any kind of case where you're making a comparison. If the distribution is in fact normal, then because that standard deviation has a consistent relationship to the data set overall, we can then say, well, okay, student in class section A got this grade, student in class section B got that grade, but they're both one standard deviation from the mean, which means that those students are essentially performing at about the same level, right? At least with respect to their particular class section. Now, where does this come up in journalism? In my case, it's come up where we actually, in a project I worked on, where we actually were grading Wall Street analysts, right? So we wanted to see how well they performed in making stock picks. We could actually say, well, this person, was a little bit ahead of this other person, but if we look at it as a distribution, we can say this person was really, really good compared to everyone else in their section, whereas the number one person in another one might have been just a little bit ahead. In any case, these are sort of the fundamental concepts of central tendency and spread that we've now talked about for both skewed distributions and standard distributions. And as I said, we'll look at some more examples next week. And then following that, we're going to look at moving away from Excel and spreadsheet, well, this kind of spreadsheet program, into something called OpenRefine, which is a really, really powerful tool that's going to let us quickly do a lot of the kind of work that we often need to do to clean up our data sets, since clean data is the rare bird in data journalism. All right, if you have any questions, please post them to the Piazza. I look forward to seeing you all next week.